I'd like to thank the ICRA committees for giving me the chance to present our paper, entitled, An Onboard Framework for Staircases Modeling Based on Point Clouds. Staircases are a critical challenge for robots coexisting in human environments. Our goal is to achieve real-time parameter modeling and pre-planning of traversable regions for robots in staircase scenarios. Current efforts largely focus on using visual methods to tackle staircase scenes, but their parameter modeling isn't up to par, failing to navigate robots effectively. Traditional point cloud methods heavily rely on the geometric structure of stairs, reducing their generalizability. Light impacts the quality of point cloud imaging, and low computational efficiency of modeling, both hindering robots' quick and robust navigation through staircase environments. Our contribution lies in introducing an end-to-end framework for real-time instance segmentation and parameter modeling of staircases. The pre-planned point sequence output from this framework can directly guide robots through staircases. We propose a series of data augmentations and a curvature-suppressed cross-entropy loss to improve network performance. To mitigate modeling errors introduced by varying views, we enhance accuracy through alignment techniques. Additionally, we have collected a dataset with corresponding annotations for near and far views of staircase scenes. We have also developed evaluation criteria specific to this scenario. Our work focuses on two phases, training and inference. During training, the data augmentations are employed to enhance dataset diversity and improve generalization. The CSCE loss function enhances the network's discriminative ability. During inference, the results are used to extract central point sequences, solve for staircase parameters, and after measurement correction, can be used to stitch navigable areas as the output. We utilize 5 Gaussian-based data augmentations to enhance the network's robustness. Randomly removed steps and random ball sampler are primarily used to improve the network's robustness against point cloud damage caused by lighting. Randomly removed non-steps aims to increase dataset diversity. Random Gaussian perturbation is employed to enhance the network's tolerance to depth errors in point clouds. Randomly remove points within groups is implemented to average the point cloud density distribution, enhancing the network's robustness when dealing with uneven point cloud density samples. During our network training, we observed a tendency for the network to favor one class over the other when faced with two classification boundary points. To address this, we introduced a curvature-suppressed cross-entropy loss function to penalize misclassified points. This penalty not only accounts for misclassification based on labels but also incorporates penalties based on the normal vectors. Staircase detection is accomplished using PointNet++ network, striking a balance between computational efficiency and inference performance. Various classified tread point cloud planes are fitted using the Ransack algorithm to calculate normal vectors. The average of these points is then computed to derive central point sequences for multiple treads. The optimal central points pair are used to infer the physical parameters of the staircase based on geometric relationships. The PCA is applied to the tread or riser to calculate their principal component vectors, from which a rotation matrix is derived. This matrix is used to correct the calculation results. Our collected dataset comprises various types of staircases, including RGB information, normal vector information, physical parameters, and labels. For this framework, we have proposed a series of evaluation criteria, including errors in central points, normal vectors, and physical parameters, as well as the error rate in staircase classification. In experimental testing, we measured the actual effects of the data augmentations and the loss function on the validation and generalization sets. The DE measurements indicated a significant improvement across all data augmentation methods and loss functions. In false positive measurements, augmentations such as RRNS, RBS, RGP, RRPG significantly reduced the FP rate. In false negative measurements, CSCE loss and RRPG reduced FN to 0. Performance on the generalization set further confirmed the significant effects of algorithms like RRS, RRNS, RBS on items DE, FN, and CPE. In comparison experiments conducted on the validation and generalization sets, our method outperformed the baseline significantly in 4 comparable parameters, with only a slight difference in item DE compared to the baseline. For a visual comparison, please refer to the right contrast video. Our method demonstrates superior performance in terms of accuracy and error rates, with higher computational efficiency. We conducted tests in a real-world environment using the RealSense D455 sensor. The input on the left undergoes downsampling and framework prediction modeling to produce the results on the right. Red represents treads, blue represents risers, and green arrows indicate plane normals. The image coordinates in Open3D and camera coordinates are not aligned. The actual results fully demonstrate the real-time segmentation and parameter modeling effectiveness of the network. In the simulation testing for navigating robots through staircases, we used the central point sequence of the staircase as a pre-planning sequence to guide the robot. This framework can reliably navigate robots through staircase scenarios. In summary, our system maintains an advantage over the baseline in terms of accuracy and generalization across various tests, while significantly improving computational efficiency. The system's output can be directly used to guide robots through staircase scenarios.